Hello there. So I understand that students sometimes find logarithms difficult, so here's a video to help with that. So when you study logarithms at school, here are the type of things that we need to learn about. We need to know the definition, but also the properties of logarithms. And often students find that part especially difficult. So here are some of the common struggles that students faces. One is that they find it difficult to manipulate the properties of logarithm. But also, it's quite difficult to understand the intuition and the purpose of logarithm when we only look at the properties. So, there will be two videos. Each will be highlighting the different perspectives of logarithm. For one, that will tell us how to manipulate the properties, and two, the history and the application, the intuition behind logarithm. So the short summary for the two videos in the future will be, the first one being that logarithm is like the movement from A to C. And the second video will be about logarithm in general is about the order of magnitude. This will make more sense as we go through the video. So let's start with something nice. What is 2 to the power of 3? Well, that's equal to 8. So then we can now do the reverse of this question. What power of 2 gives us 8? Well, we know it's going to be 3, and we use logarithm that basically does this question for us. So log 2 of 8 means what power of 2 gives us 8? And that's equal to 3. In general, we write 8 to the power of b as that. And similarly, what power of a gives us c? Well, we denote that as log base a of c. And so what log base a of c represents is the power, or the exponent, of a to get c. And we sometimes call this that logarithm is the inverse of exponents. Okay, so let's go through some examples. So we know that log a of c is the exponent of a to get c. So what exponent of 2 gets us 8? Well, that's going to be 3. So log base 2 of 8 is 3. Similarly, the exponent of 2 that give us 2 is going to be 1. And finally, what exponent of 2 give us 1? That's going to be 0. So that's what log means. So let's see if there's any other things that we know about logarithm. Well, log base a of a should be 1. Well, that's the same thing as saying what power or exponent of a give us a. And that's obviously a to the 1 that give us a. Another one. Log base a of a to the c must be c, because what power of a give us a to the c, which is of course c. And finally, a to the power of log base a of c must be c. Why? Because log base a of c is the exponent of a to get us c. So this follows strictly by definition. So we've now described the definition of logarithm. So let's now try to explain the properties of logarithm using one of the perspectives. We said earlier that log base a of c is exponent of a to get to c. And so, a to the power of log base a of c is by definition c. Instead, we're going to use a new notation now to say that log base a of c is the movement from a to c. Because when I have a to the power of this moves the a to c. And as we will see, this new notation will help us understand many of the properties. So, we'll now see how this notation will give us all of these properties pretty much for free. Okay, so let's try to prove that log base a of c is equal to log base a of b times log b of c. Well, let's firstly rewrite this using our notation. So, using a new notation, we see that to go from a to c is the same thing as going from a to b times by moving from b to c. And I think that makes a lot of intuitive sense, but this is not a proper proof as we haven't fully explained why there's a multiplication going on here. Of course, it could be an addition, and therefore we will explain this more properly later in the video. So, by using this new notation, let's now prove that log base a of b to the c must be equal to c times log a of b. Well, by using the new notation, we get that. And we could imagine separating this path into two smaller paths. One, we move from a to b, and then we go from b to the c. And this, by definition, must be equal to c, because this is the exponent of b to get b to the c. Here, pause and have a think how you might prove that log AB times log BA is equal to 1. And one way to do this is to use this notation and then simplify that two paths that we have here. Good luck. So here, let's try to derive the power rule properly now. Well, we can now take the exponent of both sides. So, a to the power of log AB times log BC, by using the power rule for exponents, we can put a bracket here. And notice this bracket inside, by definition of logarithm, simplifies to b. And again, by definition of logarithm, b to the power of log BC will give us c. So this exponent here moved us from a to c. And that is the definition of logarithm base a of c. So to summarize, there were two things we learnt. One is the definition of logarithm, and two, which is one of the perspectives, which is understanding logarithm in terms of movement. If we go a little bit more in depth, by definition, we have these two results. And by using that perspective of logarithm and the movement, we got these three properties pretty much for free. To reiterate, understanding logarithm as a movement helped us derive some of the properties of logarithm. But however, just like any perspective, there are limitations. And one of the biggest one is trying to derive the product rule. So let's see how we can use this perspective to derive the product rule. And the big warning is that it's going to use a lot of algebra, and you will see that it's not the best way to understand the product rule. I will remind again, there will be a lot of algebra, so you have been warned. Well, to prove this, let's start with the left side. We can separate this into two paths, A to B and B to BC. And this path over here can be proven to be equal to just 1 plus B to C. If we accept that for the moment, then we can combine that result so that we have this over here. And if we multiply the bracket, we see that on the last term, we got two paths here, which simplifies to A to C. Now, I went through this very quickly because actually we're not going to bother with a lot of this derivation, as in another video, we'll talk about a more natural way to derive the product rule. Now, let me show another, perhaps slightly simpler proof of the product rule. Well, we can take the exponential of A to both sides, and we see that this left side actually simplifies to just BC. Well, B can be represented by that, and C can be represented by that, by definition of logarithm. And when we have two products, we want to add the exponential. And therefore, this exponential here is equal to this. Notice we use a property that is the product rule for exponentials. Now, as simple looking as this derivation is compared to the previous one, it's always worth thinking if there's any other perspective, any other way to understand logarithm that will help us remember this. So mathematics, just like life, having multiple perspectives is very important. And one good example in mathematics is about trigonometry. We initially learned about trig in GCSE, sine and cosine, in terms of triangles. Well, we know that sine is equal to opposite over hypotenuse. However, we then extended this notation into circles, as by using circles, we can now define negative values for sine. Furthermore, we may have encountered a more interesting definition of sine using the series, and this can help us derive some other powerful properties of sine, such as e to the ix is equal to cos x plus I sine x. The point is, the beautiful and the tricky part of mathematics is to handle these different perspectives together so that we use the useful definition at the right time. Okay, I put some questions over here, so if you wish to, you can have a go at these. Cool. For next video, we'll give the other perspective, that logarithm is actually about the order of magnitude, and we'll see how that perspective will let us derive the product rule much more easily. See you next time.